Hello, hi everyone. Today we are going to see implementation of Boolean expression using NAND gates, that is universal gate, in lecture 2 Digital Principles and System Design, and this is Dr. Benila. So NAND gate is said to be a universal gate because any basic logic gates like AND, OR and NOT can be implemented using it. So implementing NOT gate using NAND. So this is NOT gate. So here if X is given as an input, then X bar will be the output, and this is going to be the single input gate. So how can we implement this using this NAND is, so this is NAND gate. So X is equal to X into X bar, X into X whole bar. So in your NAND gate, what is your NAND gate? So this is going to be your NAND gate. So NAND gate is nothing but X and Y is going to be your input now. Your output will be X into Y whole bar. So here since both the inputs are X, so X into X whole bar, so which is nothing but your X bar. Implementing AND gate using NAND gate. So AND gate is nothing but if X and Y, this is two input gate, so X and Y is going to be your input, then X into Y is going to be the output. Let's see how we'll be able to get the same output using your NAND gate. So X and Y if is your input, then your output is going to be X into Y whole bar. So but I need the output as X into Y. So I have X into Y bar. So if I connect NOT gate in the output, I will be able to get the AND gate X into Y. So we will be able to obtain the AND gate using your NAND gate. Similarly, implementing your OR gate using your NAND gate. So this is your OR gate. X and Y is going to be the input. X plus Y is going to be the output of your OR gate. So let's see how to get this using your NAND gate. So X and Y is your input means, so the output will be X into Y whole bar. So as per De Morgan's theorem, X into Y whole bar is nothing but X bar plus Y bar. But I need only X plus Y. So if I give the input as, if I give input as X and Y, I will be getting it as X bar plus Y bar. Suppose if I am going to give input as X bar and Y bar, then I will be getting my output as X plus Y. So what I will do, I will be connecting the NOT gate in the input. So X, Y, so the input to the NAND gate will be X bar and Y bar. So the output will be X bar into Y bar whole bar. So as per the De Morgan's theorem, X plus Y. Right? So this is how we will be able to retrieve the basic logic gates using your NAND gate. Now let's see the procedure for NAND implementation. First, we have to draw the logic diagram for the Boolean expression using the basic logic gates. Then convert all AND gate to AND invert, and then convert OR gate to invert OR. So to convert into a NAND gate, because if you have your AND gate, suppose this is going to be your AND gate. So if you have your AND gate, if I just introduce your bubble here, then automatically my AND will be converted into a NAND gate. That's why it's called as a AND invert. Right? Similarly, OR gate. So invert OR. So you know very well. So if I give your input as OR gate as X and Y, what happens? I will be getting your X plus Y. Suppose if I give your OR invert OR, so if I just give your bubble here, so what happens here? So bubble here means I will be getting my value as X bar plus Y bar, so which is nothing but your XY whole bar. Okay, so I will be getting the NAND gate. So invert OR and then your AND invert is going to be your NAND gate. And then once I introduce the bubble to convert your either AND to NAND or to your invert OR, so compensation I should give so that the value of your expression will not be changed. So I should make sure that each and every bubbles have included is compensated. Then convert all the AND invert and invert OR to NAND gate, then NOT gate to a single input NAND gate. So all the expressions of all the gates will be in terms of your NAND gates. So let's solve a problem here. So realize the function f is equal to ab plus cd using your NAND gate. So first procedure is, first we have to draw the logic diagram of this expression using your basic logic gates, that is AND, OR and then NOT. So for AB I will be using your AND gate, and then for CD I will be using your AND gate, and then AB plus CD. So plus will be having your OR gate. So this is going to be the function here, right? So this A and B, I will have your AB here, then this is going to be your C and D. So the value is going to be CD, and then by adding these two things I will be getting your F, which is nothing but AB plus C. Now first step in your NAND implementation is you have to convert AND to NAND first. So if you want to convert the AND to NAND, so very simple thing. So what is the thing here? So I have to introduce a bubble here, right? So if I introduce your bubble, then automatically my NAND will be converted into, AND will be converted into NAND. So since I have introduced your bubble, I have to give the compensation at the other end. So I am just compensating immediately. Immediately I will compensate. So next is this another one AND gate. So totally you have two AND gate. First I will complete the AND gate first, right? So here I will be introducing a bubble. So here if I introduce a bubble, then automatically I have to compensate the bubble here. So compensate this bubble here. For compensation, the other end I have to do it, right? So now what happens here? So NAND gate is converted into AND gate is converted into a NAND gate. So here AND gate is converted into a AND gate is converted into a NAND gate, and here this OR is going to have the bubbles here, right? So compensation bubble I have given already. So now you know that second step is to convert your OR gate to a NAND gate. So when you will be getting your OR gate to NAND gate, invert OR is nothing but your NAND gate. So here only one OR gate is there, and then it has two inputs, and two inputs it have already the inverter. So I no need to introduce anything here. So automatically this invert OR will be your NAND gate. So I will be getting this invert OR. So now all the gates in this logic diagram are NAND. So this is called as a NAND implementation. So we will be solving one more problem. So here they have given the Boolean expression in the question here. Suppose instead of this one, if we are going to have simplify f of x comma y comma z is equal to summation of minterms using K-map and implement using your NAND gate. If it's so, you have to find the expression using coordinate map. So this is going to be a 3 variable coordinate map x, y, z, and then x bar x, y bar z bar, y bar z, y z, y z bar. And what will be the value of this cell here? So for cell it's going to be 0, 1, here this is going to be 2, then this is going to be 3, 4, 5, 6 and then 7. And you know it very well. So now we will place the minterms, right? So 1, 2, 3, 4, 5 and 7. So this is the case here. We have to go for the grouping here. So first we have to check octet. So here octet is not possible, so I can go for quad. So 1, 3, 5, 7. So I can group this one 1, 3, 5, 7 to have a quad here. So next one I can have your pair. So what is the pair for this one? So I can go pair for 3 and 2 is the adjacent one. So I will go for the pair, and here 4, 5 is going to be another pair. So now I have included all the minterms here. So now I can write the equation here. So f is equal to, so this quad x bar x will get cancels with each other, y bar y will get cancels with each other. So the left out value is going to be z. And then here the next one is x y bar. So in this one what happens? You have your x, and then y bar will be y bar, z will get cancelled, so x y bar. Next for this pair you have your x bar, and then here y. So x bar y, z will get cancelled. So your expression will be f plus x y bar plus x bar y. So now I got the Boolean expression. Now I have to implement using your NAND gate. So for that one, the first step is I have to write the draw the logic diagram using the basic gates, right? So here I'll get your x y bar AND gate, x bar y another AND gate. I'll combine all these together using your OR gate. So x, y bar, right? So this is x and then I have introduced the NOT gate, so x, y bar I got it. Then I'll go for x bar y. So x bar y. So now I have your z here, right? So now I have to combine all these things using the OR gate. So I have combined the OR gate here. So now I'll be getting my f here. So this part will be having your x, y bar, and here it's going to be x bar y, and here it's going to be z. So addition of all these things will be your f. So now the first step I have finished. Second thing is I have to convert all your AND to NAND. So simple thing is I have to introduce a bubble here, right? So introduce a bubble. So if I introduce a bubble, I have to give the compensation at the other end. So I am just giving the compensation on the other end. So here I have one more AND gate, so I just include the bubble here, and then I will be giving the compensation here. So now what happens here, all the AND gate will be converted into a NAND gate. So all the AND gate is converted into NAND gate, and I have the bubble in the two parts here. So third thing is I have to convert your OR gate to the NAND gate. So OR gate is converted into NAND gate as inward OR. So here in this only one gate I have, and then in this gate I have 3 inputs. So all 3 inputs should have inward. So these 2 inputs have the input, the third one is missing. So what I can do, I can introduce a bubble here. So if I am going to introduce a bubble, then automatically I have to introduce a NOT gate at the other end. So as a compensation. So now what happens, I can convert this inward OR as NAND gate. So the last step is I have to convert all the NOT gate into a NAND gate. So single input NAND gate is nothing but your NOT gate. So single input NAND gate will be replaced. Replace the NOT gate. So now all the gates are in NAND. So this is going to be the NAND implementation. So here I have given some problems for practice here. So you can practice it. Thank you guys. Have a nice day. Subscribe my channel for automatic updates.